Welcome to Injection Attacks Reloaded, tunneling malicious payloads over DNS. I'm Philipp Geithner, and I'll present to you today our paper, which was originally published at the Usenix Security Conference this year. So our general idea, or the general motivation for the paper was that the general internet principle is to be strict when sending and tolerant when receiving. And the DNS, domain name system, generally follows this principle by meaning that the validation of anything like the record, format, etc., must be handled by the endpoints, i.e. the applications. And if you have like a new record type, the resolvers don't have to understand that. And so our question for the paper was if we could abuse this DNS transparency principle for attacks like typical injection attacks, like the SQL injections you probably know from, like, here's a comic, but yeah, you hopefully know SQL injections. So here's what a typical DNS resolution chain looks like. First, we have like an application which triggers a query because it wants to know something from the DNS. Like it wants to know the address of a server, but you can also store other things in the DNS, for example, like the SPF policies, etc. Then this query gets forwarded to the name server. We don't really care for the process where it comes to that. And the name server then provides the record in the wire format of the DNS. And essentially, this can contain any value. So in our case, we essentially assume that the name server is the attacker, so anything can happen here. This then gets forwarded to the resolver, and the resolver trusts the data transparently. Essentially, it just looks if the response is to the query which was sent, but it doesn't do anything else. And after that, the response is essentially decoded by the stub resolver or another DNS library, which translates the wire format into the textual form, so the application can handle it. Sometimes they also have more complicated APIs, but doesn't really matter. And in the end, the application handles the data. So now what is the problem? And we will first look at DNS resolvers. As I said, resolvers should and do typically handle data transparently. And the problem here is kind of that there are two formats for domain names, essentially. You probably know the text format, which is just like google.com, maybe the leading or the dot in the end, whatever. But there's also the wire format. And in the wire format, it's actually different than in the text format, where in the text format, you have like strings and then you have the dots, and these dots separate labels. But in the wire format, you have a list of labels and the length of each label is prepended to the label. So in this example here, for example, in the above one, we have Google, which has like the label 6 because Google is 6 bytes, then Google, and then label 3 because com is 3 bytes, and then 0 because the list ends there. And so the question now is essentially, what happens if we do weird stuff with these labels? For example, you can put 0 bytes in the labels, and some applications might not be able to handle that. And you can also put period signs inside labels, which is a special weird case for DNS, because as we said, in the wire format, the dots, which in the text form separate labels, in the wire format, you can actually have periods or dots inside labels, which would result in this weird example in the bottom, where you have only one label, which has length 10 and which says google.com, and not like two labels, Google and com. So what can you do with this? Essentially, we constructed an attack, which is really simple, when it exploits essentially the 0 byte, where we have a domain name which is controlled by the attacker, because that's because it's called attacker.com, and this cnames to domain victim.com. Essentially, a cname is just an alias, so you just forward it to another domain. That's not really the point. But then after victim.com, we essentially add a 0 byte, and then we add .attacker.com, which makes this a subdomain of attacker.com. And as I said, in the DNS format, this is a totally valid domain name. So it's just like, this is essentially a label which is called com, and then there's a 0 byte, and then there's the next label, which is attacker. And then we have this domain again, which, since it's a subdomain of attacker.com, the attacker can specify its IP address. In this case, it's 6666 because it's the attacker. And our attack now works by essentially we are querying for attacker.com, making the resolver process this chain, and then we are asking for victim.com. And maybe the resolver essentially misinterpreted the 0 byte for a string terminator, because in C, 0 bytes are string terminators. And if it is vulnerable, then it will answer with that victim.com has the IP address 6666, even though that this domain has nothing to do with victim.com, essentially, in DNS terms at least. And so now you would say, okay, but this will never work, right? And you're kind of right. We tested like the well-known implementations like bind and unbound, and they weren't vulnerable to this. And we also tested some public resolvers like Google and Cloudflare, and there was one vulnerable, but only in a corner case, which is now actually defunct. So this is also not an issue anymore. However, then we tested the general internet, and by the general internet, I mean open resolvers, and found that 8% of those open resolvers were actually vulnerable to this attack, which is weird considering that we haven't found any vulnerable implementations before. And so currently, actually, we are evaluating this, and our data suggests that the problem relies in forwarders, essentially the DNS stub things you have in your home router. And we bought many routers, as you can see in the picture, and stay tuned for the results of that. That was not part of the original paper. And so now that we essentially looked at forwarders and resolvers, the actual problem, or the actual more depth issue here, is in stub resolvers and applications, in our opinion. Because there's another issue in the DNS, which is the domain name versus host name problem, as we call it. And what it is essentially that the POSIX standard specifies that stub resolvers operate on host names. But the problem is that the POSIX standard doesn't actually define what a host name can be. It only defines that a host name is represented as a C string, because that's how the library works. And so if you want to know what a host name is, you have to look for an ancient RFC, which actually doesn't even, is part of DNS because it's before DNS was even standardized, which says that a host name can only be like alphanumerical characters. And that's actually maybe the rule you know, or you don't know, it depends. However, anyway, we can conclude from that that the stub resolvers, since it operates on host names when it speaks to the application, should validate that a name, when it gives it to the application, should be a valid host name, right? Well, we checked that, and it's essentially only true for one resolver, which is glibc. It does this since 1998, I think. And none of the others do that. And we also found that 7 out of the 10 stub resolvers we tested actually misinterpret our 0 byte or dot period injection payloads, which might be linked to the thing that we found vulnerable resolvers in the wild, but it's not quite sure, because typically stub resolvers don't contain caches and you shouldn't build a recursive resolver with them. So it's kind of weird. Anyway, so we now know that stub resolvers and resolvers aren't handling the validation, essentially, which is kind of expected. So the applications have to do it. The problem here is that from an application developer standpoint, it's kind of unclear, because first, the DNS data kind of seems to come from the operating system. You're doing an operating system call like get address info or something. And also the application developers typically don't know that much about DNS. They don't know that there's this host name and domain name thing, and that maybe resolvers on different OSs behave differently. So we tested essentially how applications validate DNS input, especially when considering host names. And in our study, actually none of the applications did any special validation in terms of that they tested that the host name is a valid domain name is a valid host name. And we found 8 applications have kind of exploitable vulnerabilities due to this. So you might ask, okay, what makes an application vulnerable or exploitable? Because as I said, none of them validate, but that doesn't mean that everything is exploitable. Essentially, it comes down to that the attacker first must be able to trigger a DNS query to a custom domain with the application. Otherwise, you have to do cache poisoning, and then you're doing an attack to do an attack. So it's not really an issue anymore. And the other thing is that the query result must essentially be used out of context. So the attacker makes a query to his own domain, and then you must have a different transaction which kind of uses the old data again, because otherwise the attacker can only essentially do weird stuff with his own transaction, but he can't actually affect anything else. We have some example vulnerabilities here, which we found. For example, we found a cross-site scripting vulnerability in OpenWrt, where you can inject JavaScript and essentially control the router with that. And we also find a configuration injection in RedSec proxy, which is a radius proxy, typically used in EDROM, where you can essentially inject things in a dynamically generated configuration and essentially do anything the configuration can do. For example, crash it or unauthorized network access. So our conclusions are essentially that first, that this is a problem and it's not really known, and that the standardization for stub resolvers is kind of lacking because the POSIX standard only defines host names, but it doesn't really says what a host name can be. And we find that there's a lot of missing knowledge between the DNS formats and what they can be and what they cannot be, and essentially what component in the resolution chain should do the validation. And the problem here is that since nobody really knows who should do it, it can be that nobody does it because everyone essentially thinks that someone else is doing it, which creates a problem. In terms of mitigations and patches, we reported the vulnerabilities we found, which led to some CVEs you can see here. And we are currently pushing for format checking and stub resolvers, since that's essentially the point in the resolutions chain. You can say, okay, that's still end-to-end because it's still on the endpoint, but you don't have to change every application in the world essentially to add validation to it. And you can read our paper and also test your resolver for the cache overriding or cache poisoning vulnerability at our website. And otherwise, that's the end of my talk, and thank you for your time.
And we have Philip with us now. I have at least one question ready and queued up for you. Philip, I'll go ahead and ask that. It's from online from Michael Doherty. Yes, do you have a list of the stub resolvers that are vulnerable along with the vendor platforms of that 8% that failed in your test? And I would maybe add to that. Presumably you maybe reached out to at least some of them. What was the response to your findings?
So you have to differentiate between the 8% and the stub resolvers. So the stub resolvers we tested like in our lab, and to them we also that was implementations like glibc and actually also the Microsoft one in Windows. And we reached out to them, and some of them there was different some of them essentially said, yeah, that's the thing, and actually although some of them didn't really consider it a vulnerability. We haven't really reached out to the open resolvers, so the 8% you're referring to, so what we are doing is we are doing this router study currently, but it's not like, we could use the Whois database maybe to find an administrator and say, okay, we test the DNS resolvers in your network, but it's kind of complicated to do that, and yeah, so. Essentially, we communicated to the implementers, but we haven't communicated to any operators as of now, at least not for the resolvers. Okay, and I'm seeing no more questions online or in the queue. Even the most finely assembled and presented talk before lunch is a tough time for getting people en masse to come up to the queue. So with that, we'll thank you once again. Thank you very much for presenting here at NANOG. Yeah. Applause.